Hello friends, in this video I'd like to solve the following problem from the Turkish Mathematical Olympiad final round 2005, problem number 4. Find all non-negative integers k, m and n such that 5 to the power of m plus 7 to the power of n equals k cubed. A very classic and beautiful number theoretic Diophantine equation. So my hints for this problem, it's all about reductions, modulo something. First of all, you can pretty easily guess the parity of k, and then you can consider reductions, first modulo 8 and then modulo 7, which will hopefully show that 3 must divide m. So in other words, m must be divisible by 3, and that allows us to factorize this difference of numbers because we have difference of cubes. And then factorize it and think about, can both of the factors which you get, can both of them be divisible by 7? And finally reduction modulo 5 might be helpful. So give this problem a try and I will see you in a minute. Okay, so I hope that you've managed to solve it. First of all, let's notice that 5 to the power of m and 7 to the power of n are odd numbers, and we know that sum of two odd numbers is even, so k must be even. K must be even, which implies that k cubed must be divisible by 8. And that suggests a first reduction modulo 8. Reduction modulo 8. Let's take a look. After reduction modulo 8, our equation becomes 5 is congruent to minus 3 modulo m, modulo 8, and 7 is congruent to minus 1 modulo 8, and the right hand side is, as we know, divisible by 8, so it's congruent to 0. And now think about, when can this happen? If you take a look, minus 3 to the power of m is either congruent to 1 if 2 divides m, or it's congruent to minus 3 if 2 doesn't. Why is that? Well, see the pattern. Minus 3 to the power of 0 is 1, minus 3 to the first power is minus 3, minus 3 squared is 9, but 9 is congruent to 1. And you see the pattern. Similarly, minus 1 to the power of n is either congruent to 1 or minus 1. It's congruent to 1 if n is even, and it's congruent to minus 1 if n is odd. Okay. And now look, when can sum of one of these numbers and one of these numbers, when can this sum be congruent to 0? Well, the only possibility is that here we have 1 and here we have minus 1, which allows us to deduce that 2 divides m and 2 doesn't divide n. N is odd. And one more obvious thing, which will be useful, since 2 doesn't divide n, well, n must be greater than or equal 1. It's obvious, but it's worth to point it out. Now we know something. The more you know, the easier the problem becomes, usually, not always. Next, reduction. Well, we have reduced our equation modulo 8. What other reductions might be noteworthy? Well, since we have 5 to the power of m and 7 to the power of n, reductions modulo 5 or 7 may be helpful. In this case, reduction modulo 7 will be better. So let's do it. Reduction modulo 7. Let's do it. What do we get? After reduction modulo 7, take a look. Here we have 5 to the power of m. 5 is congruent to -2 modulo 7. And then we have 7 to the power of n. It's congruent to 0. Why? Because n is greater than or equal 1. So maybe write it. That implies that 7 does divide 7 to the power of n. And the right hand side is congruent to k cubed modulo 7. And again, let's do the same checking. What are the possible residues on the left and on the right hand side? Well, it's pretty easy to see that -2 to the power of m is congruent to one of the following 6 numbers. It's congruent to 1 if m modulo 6 equals 1. If equals 0. I will copy it because I'm lazy. Okay, it will be congruent to -2 if this remainder is 1. It will be 4. It will be 4 if the remainder is 2. Okay, it will be -1 if the remainder will be 3. It will be 2 if the remainder is 4, and it will be finally -4 if the remainder is 5. You can check it manually, it's pretty easy. And then -2 to the power of 6, -2 to the power of 6 is 64, and 64 is again congruent to 1, and the cycle repeats itself. Okay, and on the right hand side, let's take a note that 0 cubed is congruent to 0 modulo 7, obviously. Plus -1 cubed is congruent either to plus or -1. Plus or -2, here's the crucial part. 2 cubed is 8. 8 is again congruent to 1. And plus or -3 cubed is 27, and 27 is congruent to -1. So here we have -+1 modulo 7. And remember that these two sides should be congruent to the same number. And that can happen. Look, 0 doesn't appear on the left-hand side, so we must have plus or -1. And that happens in this case and in this case. So either m is congruent to 0 or 3 modulo 6. Which means that that 3 is divisible, that 3 divides m. Okay, very nice. Now let's take a break from reductions and let's go back to our equation. Our equation was 5 to the power of m plus 7 to the power of n equals k cubed. And now let's do the following. 7 to the power of n will stay on the left hand side, and here I will write k cubed minus 5 to the power m over 3 cubed. And I know that this exponent m over 3 is integer because 3 divides m. And now a well-known factorization will be useful. So we have the following. Okay. And now, as I suggested, now in this type of problems, usually, not always, but sometimes it happens, that both of the parentheses cannot be at the same time divisible by 7. And in this case, it will be exactly that. So let's investigate it. So let's investigate question. Can 7 divide both parentheses at the same time? I will show that in fact this cannot happen. Why? Because because of what? Because we can take our second expression. And do a well-known trick, namely, I will write it in this form. And here, first three terms are k minus 5 to the power m over 3 squared plus 3 times k to the power k times 5 to the power m over 3. And now look, if this is divisible by 7, and this is also divisible by 7, then that would imply that 7 must divide 3k 5 to the power m over 3. But of course power of 5 is not divisible by 7, 3 is not divisible by 7, so 7 must divide k. But remember that 7 divides k minus 5 over to the power m over 3. So 7 divides this number, 7 divides this difference. That would imply that 7 divides 5 to the power m over 3, which is impossible. Contradiction. It's a contradiction. So now we know that at most one of numbers k minus 5 to the power m over 3, k squared plus k 5 to the power m over 3 plus 5 to the power 2m over 3, at most one of these numbers can be divisible by 7. Okay, that's something. And now, and remember that this product of these two numbers should be 7 to some power. And moreover, it should be pretty obvious that this term is less than or equal this term. So if only one term at most can be divisible by 7, the first is less than the second, and that implies, it's crucial, it's the step that reduces our problem a great deal. The first parenthesis must be 1, and the second parenthesis must be 7 to the power of n. That's the only possibility for this to be true. Okay, very nice. And now, what can we do? From the first equation, we see that k equals 5 to the power m over 3 plus 1. And let's put it into the second equation. So we have k, no, we don't have k, we have m to the power m over 3 plus 1 squared plus 5 to the power m over 3 plus 1 times 5 to the power m over 3 plus 5 to the power 2m over 3 equals 7 to the power of n. And after some simplifications, we will get 3 times 5 to the power 2m over 3 plus 3 times 5 to the power m over 3 plus 1 should be equal 7 to the power of n. Okay. And notice that we have already eliminated one variable. Because we started with an equation with 3 variables, here we have only 2. And we are almost at the end. It's time for reduction modulo 5. Because notice that this and this is divisible by 5 in every case except one. Namely, when m equals 0, we need to check what's happening manually. So let's check it. If m equals 0, what do we get? Here we have 3 plus 3 plus 1. That's 7. 7 equals 7 to the power of n. So n equals 1. And moreover, k equals 5 to the power of 0 plus 1, which is 2. So we have one triple of solutions. So now let's consider what's happening when m is greater than or equal 1. Reduction modulo 5 will do. Reduction modulo 5 will do because we get the following. 1 should be congruent to 7 to the power of n modulo 5, and it's pretty easy to verify. We can, you know what, we can write it manually. 7 to the power of n is congruent to either 1 if n modulo 4 equals 0, it will be congruent to 2 if n modulo 4 equals 1, or it can be congruent to -1 if n modulo 4 equals 2, or it can be congruent to -2 if n modulo 4 equals 3. So we see that it's congruent to 1 only in one and only one case, in this case. So we can deduce that n4 must divide n. And that is a problem. Why is that a problem? Well, n should be divisible by 4, but if you remember, at the very beginning, we have established that n must be odd. No number n can be odd and divisible by 4 at the same time. So, no solutions. There, because m doesn't divide n. So it's a type of contradiction. So we have only one triple of solutions. Namely, the only triple of solutions. You know what? Maybe I will some space. I will produce some space and I will write my final answer. In green, the only solution is the triple x, y, not x, y, z, but k, m, n, 2, k was 2, remember, m was 0, n was 1. Okay, and that is our answer. Our Diophantine equation has only one triple of solutions, 2, 0, 1. So as you have seen, quite a challenge. In these types of problems, it's always, or pretty much almost always, the case that some reduction simplifies or gives us information, and from one information flows the next information. And hopefully there are not that many solutions. At some point, one information will contradict other information. Reductions are very helpful. What reductions? It's not that easy to say in general case, but usually if in our problem there happens to be 5 or 7 to some power, reductions 5 or 7 may be beneficial. If we know that something is even, that cube is divisible by 8, do reduction modulo 8. There is probably no general hint to be given, no universal hint to be given, only these general hints. Okay, so I hope that you've learned something new, that you are entertained. So yes, I will see you next time. Goodbye. Thank you for watching.